So this presentation is based on three of our different papers, two published in 2023, and another one is just recently accepted by PRB. And also, I mean, all this work it was done with Professor Oscar Wafak from University of Minnesota. So this is the outline of my talk. So I will, I mean, since everyone here, I believe that is really familiar with this TBG system. So I will just give a very brief introduction on these systems. And on the second part, I will mainly talk about our recent work on how to get or how to obtain this analytic, I mean, this analytic formula to describe the lattice relaxation in this system. And in the third part, I will basically talk about our construction of the continuum field theory to describe the band structure to describe this TBG systems. Okay, so first let me just very quickly go through this the experiments, the very early experiments on this TBG systems. So back to 2017 or 2018, Professor Pablo in MIT, I mean, collaborated with his graduate student Jian Kang, I mean, to find this phase diagrams of this twisted bilayer graphene. So what they found is when the doping is at 2 and -2, we have some, we have this so-called insulating phase, and also around this insulating phase, they found this superconductivity. And very soon, quickly follow that, I mean, this, I mean, also like experiments found this anomalous Hall signals in this system when this when the doping is at +3 and is aligned with HBN substrate. Okay, and also more insulating, and also we found more insulating phases. This is at 3, I mean, when without alignment with the HBN. And so after that, I mean, many theoretical works and also many experimental works has been like published, and they try to investigate the properties of these phases. Okay, so just to give you a very like brief introduction on this on the lattice structure of these systems. So of course, I mean, everyone knows this is two-dimensional systems, and if we look at the symmetries of this twisted bilayer graphene, we know this is triangular superlattice, but different from like usual systems. We found that this unit cell is quite large. So if the twisted angle is at the magical one, I mean, each unit cell contains more than like 10,000 different carbon atoms. But if you look at the stacking pattern of these two carbon layers, we notice that it can be roughly divided by 3 different regions according to the stacking pattern. You can have this AA, so you can have this AA stacking pattern, and also, I mean, at the center of this triangular lattice, you can have AB or BA stacking patterns. Now, if we flip, so this is what happened for the rigid twist systems. If we allow the lattice relaxation, I mean, we will know that if we look at the AA stacking pattern regions, this will be reduced, and if we look at the AB and BA, it will be enlarged. And also, if we look at the energy scales of these systems, we know that the bandwidth is around, I mean, at the magic angle is around like 10 or 20 MeV, which is comparable or a little bit smaller than the interaction energy scale, which is also about 20 MeV. So the first thing to ask is why there is a lattice relaxation and how can we describe the lattice relaxation in these systems. So if you look at all those works, all the theoretical calculations for this lattice relaxation, you notice that almost every work contains 2 different energies. One is so-called elastic energy. So to describe this elastic energy, what we do is, let's say we introduce this X, which is a true position of the carbon atoms, and R describes this original position of the carbon atoms. And the difference which is U, which is basically the lattice deformation of the carbon atoms, and it can contain so-called translation or twist or rotation or this lattice relaxation. Well, this J is basically labeled the layers. Okay, and also since we focus on these two different layers, I mean we can always introduce so-called symmetric part and then this anti-symmetric part of the lattice relaxation. Now, if you look at this anti-symmetric part, which is a difference of this lattice of the lattice relaxation of these two layers, it can always contain this twist part, which is rigid twist, and also the others are just called lattice relaxation. So the elastic energy, if we just substitute this formula into the expression of the elastic energy, we notice that this symmetric part and this anti-symmetric part got decoupled, and also if we look at this anti-symmetric part, it can be expressed in this way. So notice that it contains two different elastic constants, this kappa and this G. Now the kappa basically is related with only the normal stress part for the lattice relaxation, and this G, it depends only, I mean, it related with only this shear stress part of the lattice relaxation. And also, so this is so-called elastic energy, and also it competes, I mean, with this interlayer potential. So this interlayer potential basically can be expressed in this way. So we have this capital G, which is the reciprocal lattice vectors for monolayer graphene. So it turns out, if by symmetries we look at this this interlayer potential part, it basically for the first three different G shells, I mean this Vg can be described by only three different constants. Okay, so we have this C1, which basically is for this capital G1, capital G2, and capital G3, and this C2 and C3 is for the second and third G shells. Now, if you look at all the theoretical models, you notice that there exists some hierarchy structure between all these different Vg or these three different Cs. Usually what you have is the constant for the innermost shell is much larger than the second or the third shells. Now, it's interesting to know that this hierarchy structure is also inherited by this so-called lattice relaxation structure. Okay, and also I should emphasize that if you look at the C1, is always positive because this interlayer potential is smallest for the AB stacking. Okay, and also this relaxation is obtained by minimizing the sum of this interlayer potential energy and also elastic energy. Okay, so also to basically gain some concepts or to have some ideas of this lattice relaxation, it's better to focus on its Fourier transformation, which can be written in this way. Well, this small g is basically the reciprocal lattice vectors for the Morel lattice. So also it happens, so in principle, because this delta U, this lattice relaxation will focus only on the in-plane part. So it can be always described by its divergence and its curl. Okay, so interestingly, if we look at its divergence part, we notice that this delta U is almost divergence free. So why this divergence almost vanishes? Because of the symmetries. That is, if we look at the divergence of this delta U and do Fourier transformation, just by symmetries, we notice that for the three innermost shells, its divergence must vanish. So what is left is almost just the curl part. Okay, so if we only focus on the curl part, we can express this delta U just by this formulas, and this formula, if we look at this formula, it contains just three different dimensionless parameters. I mean, zeta 1, zeta 2, zeta 3. They just corresponds to the curl part of this lattice relaxation. Okay. So now we are so now we look at this I mean, this dimension, what parameters controls this lattice relaxation. So first we noted that if we look at the lattice, if we look at the elastic energy and if we look at this internal adhesion potential energy, we can have some dimensionless parameter which is C1 divided by G theta square. So this dimensionless parameter basically tells us how strong the lattice relaxation is in this system. So if we look at two different limits, so first if we look at what happens if C1 is very small, which means we can, if we can completely neglect the internal potential, so there will be no lattice relaxation in this system. And in the second case, if this G, if the elastic energy, okay, is let's say is very small, so in this case, what will happen is we don't. So in this case, what will happen if the elastic energy is very small? So what happened in this system is just we have AB and BA regions, and between these regions we have this domain wall. Now, as I mentioned, this delta U can be approximated by this expression, I mean, which contains three different dimensionless parameters, zeta1, zeta2, and zeta3. So what happens if we just look at this, the rough value of this zeta? We noted that there exists some hierarchy structures between these dimensionless parameters. So we noted that for zeta1, which describes the curve of the lattice relaxation in the innermost shell, so it's roughly given by this lambda, okay, by this dimensionless parameters. And for zeta2 and zeta3, usually they are much smaller than zeta1, because if we just look at the scale, it's about like lambda square, or it depends on C2 divided by C1 times lambda. Okay, so basically this, well, just to mention you that C2 and C1, they are these parameters in this internal adhesion potential. Okay, so usually, I mean, as I said, C2 and C3 are much smaller than C1. So basically, this tells you zeta2, zeta3 should be much smaller than zeta1. Yes. Okay. So this is elastic energy. So if we look at this one, this kappa basically, I mean, is like energy per area, right? So if we look at C1, okay, so so this one cosine is dimensionless. This one is also areal. So this Vg, which is the parameters in this internal potential energy, which is also energy per area. So it's related by this one. So at AA, so this U minus should be 0. So you have like a perfectly, yeah, yes. Okay. So we have this lambda, which gives, which basically tells you how strong this this lattice relaxation is. And so because we have this hierarchy structure between different zetas, so as a very initial step, we can just completely forget zeta2 and zeta3, and we can calculate what is internal potential energy and what is this elastic energy. So it turned out that for the internal potential energy, I mean, you have some kind of like a complicated expression, which basically is infinite sums of all these Bessel functions. But in some sense, it can be still handled. So if we expand this internal potential energy to the cubic order of zeta1, and then we minimize the total energy of this internal potential energy and also elastic energy, what we get is basically we can get the equation to solve zeta1, and this is the final expression for zeta1. Okay, yeah. In the out of plane, but in this case we neglect it. Yeah. Okay. So this gives the expression for zeta 1, which basically tells you the lattice relaxation on the innermost shell. And we can also compare it with the numerical calculation. Just directly minimize the total energy without doing much, without doing any approximations. So if you look at this plot, okay, so if we look at this red dots, this is based on the fully numerical calculation for zeta 1. And also this blue line basically is from this expression. So as we can see that from, as long as this twisted angle, this is theta, is let's say larger than 0.5 or 0.6, we see these two curves almost match perfectly. Okay, so so basically it tells you that if this theta is larger than 0.6, this expression, I mean, it's analytic, but it almost perfectly describe what is lattice relaxation in these systems. Now, in addition, if we look at this expression, okay, if we look at this expression, because of the existence of this square root, we know that if we allow this lambda to be complex, to be on the complex plane, this expression actually contains a pole on the complex plane, and if we look at the absolute value of this pole is 0.28. Now, why do I say this? Because it contains this pole on the complex plane. This means that this expression cannot be expanded as a power series of lambda as long as lambda is larger than these critical values. Now, for if we look at this critical value 0.28, and if we translate it back into this twisted angle, what happens is that this 0.8, if we translate to this angle, is very close to the first magical one, which is about 1 degree. So this basically means that if you want to describe this lattice relaxation close to the magical angle, in principle, you cannot expand the lattice relaxation as a power series of lambda, which as many theoretical work has done. Yeah. No. What I say is lambda is not complex. However, if you just expand, if you just assume lambda can be complex, it contains a pole, it contains a singularity point. So which means you cannot, even on the real axis, you cannot expand this expression as a power series of lambda, which I mean, many theoretical work has tried to do so, but what happened is if you really are interested in what happened at the magic angle, you cannot do this, because eventually this will start to diverge at or below the magic angle. Okay, so this is for the part 2. I mean, this is our analytic formula for this to describe this lattice relaxation. So in the rest of my talk, I will just want to focus on this how to construct a continuum field theory in real space to describe this twisted bilayer graphene. So if we look at all the references, there are basically two different theoretical models to give the hoppings between to give the microscopic hoppings between different carbon atoms. Now, the first one, which is a very early one, was developed by Continuum. This in 2012. So what happened is they used this Slater-Koster method, and they calculate what is intralayer and what is interlayer hoppings as a function of the distance, of the hopping distance. So this one, so if you look at this expression, now the major interesting thing is you look at all these hoppings, basically they are in-plane isotropic, so which basically means that they do not depend on the orientation of the in-plane hoppings. Now, a different one was developed by Caxiros, and this was done in 2016. So what happened is they construct this one-year state, and then they calculate what is this intralayer and what is interlayer hoppings. Now, for the interlayer hoppings, if you compare with the one by Continuum, I mean, we notice that both of the in-plane hopping or of the intralayer hoppings are isotropic, but for the interlayer, okay, so if you look at this expression, is given by Caceres. This the major or the most important thing is that this becomes anisotropic, which means this interlayer hopping depends on the orientation of the hopping vectors. Now, of course, this is a microscopic models. I mean, we want to do any theoretical calculations, we will want to deal with the interactions. We cannot start from this because it's too complicated. Okay, now it comes to the continuum model. So I will just give a very short introduction to the BM model. I mean, the one used by most of us. So if you look at the BM model, I mean, as you know, that it contains, if you look at this interlayer part, is just the Dirac, and if you look at this interlayer part, is just the tunneling given by this one. Okay, so if you look at this model, basically it contains just three different parameters. The first one is Vf, is Fermi velocity of this Dirac, and also W0, W1. We know that is interlayer, intro, and intersublattice hoppings. And also, if you look at the energy scales, for the intralayer part, this energy scales is given by Vf times k times theta. That's about 200 MeV at the magic angle. And also for this W0, W1, this interlayer hopping, the energy scale is about 100 MeV. And also, this gives you the band structure near the charge neutrality point for different W0 over W1. So notice that we already fixed the ratio between W1 and Vf theta to be around 0.6. So as you turn on W0 from 0 to this ratio, we can say that initially you have this perfect flat bands, which we call this as chiron limit, and as W0 becomes non-zero and becomes larger and larger, we see that the two bands around charge neutrality point start to gain some bandwidth, and also the band gap to the remote bands become smaller and smaller. Okay, and also we have this Wilson loop calculation, as everyone knows, and this basically shows if you look at two bands, and this basically shows you can treat those two bands and you do some superposition. It can be understood as like Chern +1 and Chern -1 bands. Okay, this is true of almost like for almost all the values of the W0 over W1. Okay, so so far, I mean, almost everyone uses this BM model in the theoretical calculations. However, if you look at the BM model, we're not quite satisfied with this because first, I mean, if you look at BM model, it's written, or if you want to do any calculations, you have to do this in the momentum space, which basically means you already assume that the whole system has these translation symmetries. However, I mean, if you want to understand, or if you want to study the effect of all these effects like disorder, like density deformation, if you want to understand all these effects which breaks the translation symmetry, it seems like this BM model is kind of, I mean, it's not useless. I mean, it's kind of like not quite suited for this purpose. And also, I mean, if you look at the original version of the BM model, we know that it's derived only for rigid twist. So if we do have lattice relaxation, I mean, of course, we have various ways to revise this BM model. But I mean, do we know? I mean, like, do we have some sense how to really include all the effects of lattice relaxation? I mean, still a question. Also, if you look at the internal tunneling part, so far it contains only 3 different Qs in the internal tunneling part. Of course, I mean, this is reasonable because if you look at the Fourier transformation of this internal tunneling as a function of momentum, we see that it quickly decay, and so that's why you only look at the first shell. And also, if you look at the second shell of all these Qs, I mean, you already decays so slow. It already becomes very tiny. Okay, but this is true only for the rigid twist. If we want to include the lattice relaxation, I mean, do we have any? I mean, do we need to change this picture? Do we have some different numbers? So far, we still don't know. Okay, now the major thing, or the most important effects, is lattice relaxation, as we know. Now, how to change this BM model to include this lattice relaxation? I mean, as almost everyone did, this is you just do some replacement. You change this P to P plus A. Well, this A is so-called a pseudo gauge field or pseudo vector field, which basically tells you what is, which basically describe or include some effects of this lattice deformation or lattice relaxation. Okay. Now, also, I mean, as we know that another important effects, if you want to include the lattice relaxation, is you change this W0 and W1. Now, usually, I mean, as we know that if you don't have any lattice relaxation, those two guys should be equal. But once you have this lattice relaxation, we know that AA regions got shrink and ABBA got expanded. So the effect of this is basically W0 becomes smaller than W1. Okay, and but how about do we need to include any other terms in this internal tunneling? So one possible thing is because of you have this lattice relaxation, which I mean, if you do Fourier transformation, you have all these different Morel G vectors. So in principle, I mean, if you look at this internal tunneling, you cannot just include the first 3 Qs. You have to include some large Q shells because those tunnelings can be assisted by this lattice relaxation. Okay, but okay, of course, I mean, all what happened, all what I just talked about is some small, and also for this internal, for this intranet tunneling, I mean, so far, I mean, we just stop at the linear momentum term. So how do we need to include the higher order terms? Do we need to include P-square terms in the intralayer part? And also in the interlayer part, so far we just include so-called vertex coupling. I mean, it's those W0, W1, they are independent of the momentum. Do we also need to include some gradient tunneling terms? I mean, so all these questions, I mean, that's what I want to answer during this talk. Now, what we found out is if you look at all these terms, if you look at the energy scales of these terms, they're small. That's true. I mean, they are usually like smaller than 5 MeV. Now, whether this is important, well, we will see from 2 different aspects. The first one is if you look at the bandwidth of those 2 flat bands at the magic angle, they're just about 10 or 20 MeVs. So this 5 MeV compared to 10 or 20 MeV, that's not a small number. Now, the second thing is, if you look at all this numerical calculation of so-called correlated states at for these systems, so for example, if you look at this so-called semi-metal, if you look at quantum Monod's Hall, if you look at this stripe phase, or even just Dirac cone, I mean, without including interactions, if you look at the energy of all this possible candidate for the ground state, the energy difference, as you can see, if you forget the last one, all the above 4 states, I mean, their energy difference is just about 1 or 2 MeV. So 5 MeV, if you compare with the energy difference of all these correlated states, they're not a small number. Okay, so I think so that's why, I mean, that's a motivation. I want to change this BM model. I want to include all these effects. Okay, so now the question is, do I have a systematic way to start from so-called microscopic time binding model to obtain the continuum model? Okay, the most important thing is the systematic way, because we want to go down to, let's say, 1 MeV energy scale. So first we still start from this so-called microscopic time binding model, which is the most general form is written in this one. And also, I mean, as I mentioned at the second part, at the part for lattice relaxation, all the true positions of the carbon atoms, they can be written in as the original position plus all this lattice deformation. Okay, which include twist and also the lattice relaxation. And if you like, you can also include the disorder. Okay, and also for the wave functions, I mean, or for this electron operators, we can basically just divide it as a summation from the contribution from value k and from the value minus k. So if you look at this EIKR, this basically is a plane wave, and this psi basically is the envelope function of the when the electrons are close to the value k. Again, we'll just and also we'll just focus on psi because we assume that there is so when the twist angle is very small, so there is almost no scattering. I mean, what I mean is one body scattering between psi and phi. So between value k and value minus k. And also one interesting thing is if you really want to write this continuum field theory, I mean, which coordinate should we use? I mean, we have two different possible choices. If you look at this expression, you can write field theory in terms in the coordinate of r, or you can write field theory in the coordinate of x. So here in this work, we choose to write in terms of the x. There is some reasons for this, because if you look at those two layers, now because you have twist, okay, so that means if you have 2 points on 2 different layers, if those 2 points have close x, they're not necessary to be close at r. So if you just want to include the local couplings, you have to write your field theory in the coordinate of x. This is so-called Lagrangian, which is for x, and the univariant is for r. So we choose to build our field theory in the Lagrangian coordinate. What? Oh, okay. Oh, yeah. I wrote this crystal and the knife frame. Sorry. So this is the formula, or this is our master equation for this continuum field theory. So I mean, I don't want to explain everything in this formula. So there are just like 2 or 3 little things I want to point out. So if you look at this continuum field theory, notice that you have this capital J. This capital J basically is a Jacobian coordinate. It's a transformation matrix between r and x, between those 2 different coordinates. And also, if you look at this T, basically this is so-called the hopping functions, the microscopic one. And this psi, dagger, and psi, I mean, as I already mentioned, they are just an envelope function, or of course that means written as an operator, but in principle they are just the envelope functions of the electrons when it's close to the value k. Now again, I wanted to emphasize that in this formula we don't have the scattering between value k and value minus k. Okay. So eventually it's written in this way. So as you can see that it contains the vertex coupling, it contains also this gradient couplings. Now, so first let's look at the interlayer part. So well, not surprising. I mean, first you contain this drag cone, and this P is replaced by so-called P plus A. Well, A is just the pseudo gauge field for this lattice relaxation. But in addition to that, we also have p square terms, which goes to the second order of the momentum. And also we have the coupling between the momentum and the so-called the lattice relaxation field. Now, if you look at this one, okay, for the model built by Caceres, we found that this the energy scale for this one is about 50 MeV, which is not small at all. And also, if you look at all the energy scales of this guy, of these so-called second order terms, their energy scale is about 5 MeV. Okay, so this is the interlayer part, and also we want to go to the interlayer part. The interlayer part, if you firstly, it can be divided into 2 different categories. The first one is so-called capital T, which basically gives you the vertex couplings, and also this second term, which is this gradient coupling terms. Now, first I want to emphasize, if you look at the energy scale of this capital T terms, that's about 100 MeV, and the second term, gradient term, which is about 5 MeV. But the more important thing is, if you look at what happened for these T terms, remember that for BM model, it contains only the sigma 1, sigma 2, and sigma zeros. But but when we built this continuum field theory for the model given by Kang series, we found an additional term which is I sigma 3 terms, which again, it does not violate any space symmetry or C2T symmetry or time reversal symmetry, or it does not violate all the symmetries, but what it violates is so-called particle hole terms, particle hole symmetries. So this I sigma 3 basically can break particle symmetry, and also this particle symmetry can be broken by these gradient terms. Okay, and also this capital T terms not just contains 3 different Qs, it can also contain some large momentum transfers. And the interesting thing, because of the existence of lattice relaxation, this large momentum transfer terms, if you look at their energy scales, is about 20 MeV. Okay, so finally, I will just compare our continuum field theory with this band structure calculation directly from the microscopic time binding models. So the left one is for the model given by Continuum, and this right one is for the model given by Kang series, and also the top one we do not include any lattice relaxation, and the bottom one is for the existence of lattice relaxation. As you can see that you can almost see no difference between the time binding model and continuum field theory for the energy scale from almost like -160 to +160. So that's about like 300 MeV. For this energy window, you will not be able to see difference. Also, another thing is, so if you look at two different models, the Continuum one and the Kang series one, and this basically plot the sublattice polarization. And in the momentum space, now you can see that for the Continuum one, if you look at those sublattice polarization, is kind of high. It ranges from 0.85 to 0.6. But for Kang series one, the sublattice polarization is much smaller. Okay, so yeah, so okay, let me explain this. So you can basically plot. So you have this sigma 3, which is a sublattice polarization operator, and you project to those two bands, and then you diagonalize. Then you just plot the eigenvalue. Okay. And the most interesting thing comes from the particle hole symmetry. Okay, I'll just jump to the result. So also, yeah, if you look at the one given by Continuum, almost everywhere in the momentum space, you can see that the particle symmetry is almost perfect. But what happens if you look at Kang series model, and especially for the points for the momentum close to the gamma point, and you will see that this particle symmetry becomes much worse. It's basically, if this eigenvalue is 1, it means you have perfect particle symmetry. But if this one becomes smaller, then particle symmetry becomes worse and worse. So this is what happened for Kang series one. Near gamma point, the particle symmetry becomes not that perfect. And also, this is a Wilson loop. How many minutes left? Okay, I will just jump to conclusion. So the conclusion is, first of all, we have this analytic formula for lattice relaxation, and also I hope that we present our systematic method to obtain this continuum field theory for TPG, and also some terms beyond the BM model are important to understand the particle symmetry and also to match the dispersion. Thanks.
Questions?
Jian, it's just a curiosity. You have a very nice analytical formula for the elastic energy in the beginning. Did you try to calculate the phonons and that come out of that?
Not yet.
Okay.
Not yet.
Okay, wait.
So your formula for the relaxation, right, contains Bessel functions. It's kind of complicated, right? If I take, let's say I take the Kang series parameters, and I neglect V2 and V3.
Yes.
Just have V1. Then I can make a very simple one shell formula that when we tested it a little bit, it's about 30%.
Sorry.
It's about 30%.
Can you repeat? Sorry.
It's about 30% or 20% error from yours. Is that something that is true? Because you said there's no expansion.
So
right?
let me try to repeat your question. So we have this. Okay.
So with Koshino parameter it's a bit off, but with Kaxiras, it's obviously not self-consistent.
So this is the expression for internal adhesion potential, right? So you say you want to cut this one, or?
Well, so I have the.
Okay. So let me be quick. It depends on how you cut it. You may get. Sorry. Let me think. Okay. So it depends on how you cut. You may get just a lambda, which basically is this. Which is this black line. I mean, if you do like a very rough cut, you get lambda.
So the rough cut meaning the potential has V1 times cosine of
yes.
If I consider that cosine, if I don't put the relaxation, that cosine, right? So there's the first zero shot basically.
Right.
I find that you get basically within 20% or 30% of the self-consistent one. Do you agree or not?
And the magic angle.
It's a matter of numbers. How you have an exact formula, but it's a bit complicated. If I want something very simple, it's about 30% off, 20% off. Is that true or not?
Well, if you just get lambda, that's about the 20%.
Okay, so you agree
at the magic angle.
Okay, good.
So which basically shows in this plot. So the 1.0, that's magic angle. So you look at the difference between this green line and this purple or whatever. I mean, the difference is about, I forgot the exact number, but it's 10 or 15%. So that's quite simple. Okay. So that basically means when you look at the gauge field, the pseudo vector field, which if you get everything, that's about 50 MeV. So now you have 10 or 15% off. So that means the energy difference is about 7 MeV.
Thank you. If you had to express your gauge fields in terms of Teslas, how large would it be?
I forgot the exact number, but I remember that's about 40, 50 Tesla. Yeah, I think we do have this in our paper. Oh, okay, sorry. Maybe I'm wrong. I forgot.
Thanks for the nice talk. So I would like to know about. I would like to know if you know the reason why the wave function for the Cassiros and Koshino seems like 60-degree rotated. I mean, I'm asking this because maybe in one model, the analog trigonal warping gamma tree effect is less pronounced than the other one. It should be something like this. I'm talking about
you're talking about the lattice relaxation, or?
I'm talking the wave function. I mean, when you show the two wave functions around the gamma point.
Okay, let me go.
Oh, yeah, you just pass.
Well, sorry.
No, not this one, for sure.
Sorry.
Yes.
This one?
Yeah, they seems like pi rotated, yes?
This is a sublattice polarization, yeah?
Mm-hmm.
Okay, I'm not 100% sure, but I know that for those two models, for Koshino's model and Kaxiro's model, the lattice relaxation at magic angle is very different. I mean, if you look at the numbers, so the lattice relaxation itself is very different, which may also affect this sublattice polarization stuff. Yeah. I mean, I didn't fully investigate how this difference comes from.
Other questions? So we thank Jian again. So there is a coffee break. We come back in 30 minutes.